Okay, class, so let me get started and remind you where we were last time. So we really started playing around with supremums and infimums. Okay? So this will be a large, part of the class, understanding properties of these real numbers. So we saw some of their properties. We'll see a lot more. So today, I'm going to really talk about consequences of completeness. Okay, which is I mentioned it in an earlier lecture, but I'm gonna say it again. So it's another axiom that we add to the real numbers. This will turn out to be what kind of differentiates what we've done so far. Well, what we're going to do, it's going to make the real numbers different than the rational numbers. So the completeness axiom says that if you have a non-empty set, which is a subset of the real line, which is bounded above, then the supremum of S exists. And in particular, it is a real number. Okay? So it's the existence of supremums. There's a similar statement if you're bounded below the existence of infimums. Okay? We'll see that this is kind of the crucial property. So for rational numbers, there will be sets where the supremum doesn't, it may exist in the real numbers, but it doesn't exist in the rational numbers. Okay? So I'm going to begin actually with what's going to be the lecture problem for Friday's office hours, which is the Archimedean property. There's a proof in Sally, okay, but he states it slightly differently than the way I state it. So it's a good exercise to prove this for yourself. So it says if x is in R, then there's some natural number. So I'm going to call it n sub x. So it's a natural number which depends on the x that you're given, so that x is less than nx. Okay, so for any real number, there's a natural number which is larger than it. Now, what you have to this is maybe obvious if you're assuming, properties of the natural numbers, but we have to derive it just from the axioms that we have. Okay, so derive from the axioms we know. That's the lecture problem. Okay, let me just say as a corollary from this is that n, the natural numbers, is an unbounded subset of the real numbers. Okay? So it follows pretty much immediately from knowing this property. Okay? Let me give you another corollary, which again will seem simple, but isn't something that we were able to show before. So if you take the set 1 over n for all natural numbers, then the infimum of this set is 0. Okay? So notice I had said before that there was kind of no smallest real number. Right? So before we had seen that there was no smallest real, positive real. Okay, And this basically came because once you knew what a positive number was and you knew that it was closed under multiplication, you could take any positive real number, divide it by 2, and that's still a positive real. But this is something saying something a little stronger, which is that if you look at the set 1 over n, there's no smallest real number which is smaller than all of these except for 0. Okay? And this really, relies on the Archimedean property. Maybe I'll just draw you the picture of what this set looks like. Okay? So let me give you the proof. So if it's not empty and bounded below, then the infimum exists. Okay? So that's kind of the first thing that we want to show, is that this set S is bounded below, so that there is an infimum. But this isn't bad to show, right? Because 0 is a lower bound. Just because all of these numbers are positive. Because 1 over n is in P for all P. Or for all n. Okay? And you can get this just from, well, we worked out before that if you take a positive number, divide it by a positive number, or multiply by a positive number's inverse, you stay positive. Okay? So clearly, the infimum is greater than or equal to 0. And what we have to show is that, there can't be the infimum here. And the natural numbers just limit to this one, or 1 over the natural numbers limit here instead of 0. Okay? So we know for any epsilon greater than 0, so this is just some real number, just typically denoted by epsilon, so I will. We know that the Archimedean property, did not spell that right, implies there is an n epsilon in n so that 1 over epsilon is less than n epsilon. And now, using compatibility of, ordering with multiplication, we get that this implies 1 over n epsilon is less than epsilon. And now this is some natural number, so this is in the set S. So therefore, this is saying that epsilon is not an upper bound for S. Okay, because we found an element of our set which was less than it. Oh, sorry, a lower bound. Okay? And now, well, this means, since epsilon was arbitrary, since epsilon was any positive real, the lower bounds must be, 0 or negative real numbers. And therefore 0 is the greatest lower bound. Okay, so this will also be, maybe I'll just write this as a separate corollary, but it's, useful. So for any positive real, there is a 1 over n so that 1 over n, okay, I'll call this real Q, 1 over n is less than Q. Okay, so this oftentimes it's kind of simpler to work with elements of the form 1 over n or, 2 over n and so on. And this is telling you that you're not losing too much. You can find, if you're interested in finding something which is close to any certain number, there's going to be a thing which looks like 1 over n, which is close to it. Okay, so let me now go to the next consequence of completeness. This is going to be kind of a larger consequence, I think. So let me give you, it's going to be lecture problem number 2, which is that the square root of 2 is not in the rationals. Okay? So that's a nice proof to work out if you've never done it before. Okay? The trickier thing, or what we'll see, is the question to ask is, why is there a square root of 2 in the real numbers? Okay? So why can we find a real number which squares to 2, and when we couldn't find a rational number which squares to 2? And it will turn out that this is really a consequence of completeness. Okay, so I'll write this as a theorem. Of course, we're not going to find, we won't find like 1.41 blah, 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 whatever the decimal expansion is. But what we can say is that there exists some positive real number x so that x squared is equal to 2. Okay? So let's look at the proof. So what you want to do is you want to find, the idea is that you want to find square root of 2 as a sup of some set. Okay? And there's a natural set to look at, which is just the positive real numbers, where, I said they're positive, and they square to less than 2. Okay? So this is going to be, you should think you're kind of getting as close. So here's 2. Here's what I want the square root of 2 to be, and I'm looking at this set S. So it's getting closer and closer to kind of what the square root of 2 should be. And then you want to say that completeness ensures that the sup is in there. Okay? So first, let's check the details. So first, is S empty? We need non-empty sets if we're going to have sups. And the answer is no, because 1 is in S. Phew! Or 0 is in S. Okay, very good. Now how about bounded above? We also need that if we're going to say that a sup exists. Yes, right? Because if, let's see, if t is greater than 2, then t squared is greater than 4. So therefore, 2 is an upper bound for this set. All right, if I take any number that's larger than 2, I know that it won't fit here. Okay? And this comes from, again, compatibility of ordering. Okay, so therefore, we have a sup. So we have an x in R, which is the sup of S. Okay, good. But of course now we have to show that x satisfies the properties that we want, right? Just having a sup isn't that good. So what we want to prove now is that x squared is equal to 2. And the way that we do that is we rule out x squared being less than 2 and x squared being greater than 2. Okay? Again, I'm going to leave this as an exercise. Okay. I think it might make it onto the next homework rather than having a third lecture problem. Oops. Okay. So how do I want to do this? So assume that x squared is less than 2. We want to find maybe I'll say an s in S so that x squared is less than s squared, which is less than 2. And what this will do is contradict x being a sup. Okay, because we found an element of s. Well, in particular, we know that s squared has to be less than 2 since it's in this set. The key thing to show is that x squared is less than s squared. Okay? And the way that you do this is that you look for x plus 1 over n for large N. Okay? That's what will do the trick. Let me try to move this up. Oops. Okay. So now you have to do some sort of scratch work, right? You have to actually make a computation. So what we're really doing is solving for n here, okay? So we know x squared is less than 2. Unfortunately, we don't really know exactly what x squared is, okay? So you have to kind of solve for the right n depending on the gap between 2 and x squared, okay? So let's do it out. So we have x plus 1 over n squared. This is what we're interested in. So this is x squared plus 2x over n plus 1 over n squared. Let me just write this. So this is x squared, and I'm going to pull out a 1 over n, 2x plus 1 over n, which is less than or equal to x squared plus 1 over n times 2x plus 1. Okay, so I've just made this number a little larger, switching it to 1. The reason I'm doing this is that, well, we're eventually, here maybe I'll not clutter that, we're eventually going to solve for n, right? So it's kind of easier to eliminate as many n's as you can. Okay? And what you want is that this, for suitable choice of n, this should be less than 2. Okay? And so what we know is that, well, x squared plus 1 over n times 2n plus 1, if this is less than 2, well, this is the exact same thing as saying 1 over n times 2x plus 1 is less than 2 minus x squared. And what we know, by assumption, this is real, okay? By assumption, this is a positive real. So therefore, well, 2 minus x squared over 2x plus 1 is less than, is a positive real number, because 2x plus 1 is a positive real number, so there is an n, so there's n and n, so that 1 over n is less than 2 minus x squared over 2x plus 1. And this is the number that works. Okay, so using this n, like we just worked it out exactly so that x plus 1 over n is in S. Okay? And this is a contradiction. So therefore, and this kind of idea will be used, throughout the rest of the course, essentially. So completeness forces the existence of the square root of 2. Okay, so you can show that, in other words, if I look at this equation, you can force such equations to have solutions in the real number by approximating them by other solutions. Okay? So, in fact, of course, as we know, or as we've seen, since Q is countable and R isn't, R minus Q, the irrationals are uncountable. So most numbers are irrational, like the square root of 2. Are irrational. And in fact, completeness can kind of show that all of these, it's going to imply that all of these uncountable number of irrational numbers are contained in the real numbers. Okay? So you might think, so this is kind of going to be a useful theorem later. Okay, so as we've seen, so Q is much smaller than R in this sense. But it's also fairly densely packed inside of the real numbers. Okay, so what I mean, this is called a density theorem. So if x is less than y, and x, y are in the reals, then there exists some rational number between x and y. Okay? So oftentimes you can kind of get away in your arguments by assuming that numbers are rational, because if you're trying to approximate some real number, you can always do a better job or do as good a job by using just rational numbers. Okay, so let me do the proof. So we're going to assume that x and y are greater than 0. There's kind of an argument that you can do if they're both negative, and if one is negative and one is positive, you just choose 0. Okay? So that's not too exciting. So what you can think of what you want to do is that we first need to find kind of the right denominator. Okay? So we need to find a large denominator which can fit inside x and y. So if x was 0, for example, and this was y, well, we've already done this, right? We already found a 1 over n in between 0 and y. And then you have to find the right numerator which pushes you in between x and y. Okay? So the way that you do that is, well, you say, well, y minus x is greater than 0. So I know that there's some n in n, so that 1 over n is less than y minus x. Okay? And therefore, we have that 1 is less than or equal to n times y minus x. So in other words, we have that nx plus 1 is less than ny. Okay, just multiplying out and moving the x over. Okay, so we now need a fact, which follows, this comes from Archimedean property plus well ordering. Okay. For any positive real number, there exists some natural number, so that this z, this real number, whenever I don't write where z is, if I just write z is greater than 0, I'm always assuming it's a real number. Okay? So this is in between nz minus 1 and nz. Okay, so you kind of, Archimedean tells you that you can find a natural number larger than z, and then you keep subtracting 1 until you get to kind of the one where it fits in between, okay, where this is an upper bound and this isn't, okay? So therefore, there exists an m in n, so now I'm going back to here, so that m minus 1 is less than or equal to nx, which is less than m, okay? You can think of my m is now going to be my numerator, and my n is now my denominator. Okay, so I'm approximating nx by these natural numbers. This just tells me now that m is less than or equal to mx plus 1, which is less than ny, and therefore m is less than ny. Therefore, we get that nx is less than m and is less than ny, and now dividing everything by n, we get that x is less than m over n, which is less than y. Okay? So this is my real rational number between them. Okay, and again, what you can think of as what we did was, well, you found the n, depending on how far x and y are spaced apart, and then you found m by moving 1 over n in between x and y. And the natural way to do that is actually you put 1 in between nx and ny. Okay, so I think now I'll just do kind of define some natural subsets of the real numbers, and then we'll see in the next lecture kind of what we can do with them, okay? So we're going to be defining some natural subsets. So the order relation is kind of a separate topic. The order relation on R determines a natural collection of subsets called intervals. Okay, so there's some varieties of these, right? So the first is open intervals, which I'll use this for my notation. I know this is the same notation as a Cartesian product, and that kind of sucks, but everyone uses it, and there's just no way around it. I mean, there is a way around it, but it's not notation that anyone else will ever use. So I will this is defined to be the real numbers that are between a and b. Okay? So usually I'm going to call a and b the endpoints of this. All right, so note that a and b are both not in the open interval from a to b. Okay? And then there's closed intervals, which are you take AB, and it's just the x in R, where A is less than or equal to this element, and it's less than or equal to B. Okay? And then there are half-open, similarly define, A to B, A, B, etc. Okay? So there's a couple other intervals that naturally come about. So for notation, we write A infinity to be the x in R where x is greater than or equal to A, and minus infinity A to be x in R x less than or equal to A. Okay? Of course, infinity is not a real number, but we're just this is our notation for these sets. Okay? So we define the length of any interval, whether it's closed or open, doesn't matter, or half open, to be just b minus a. Okay, so the open interval 0, 1 has length 1 for us. Okay, so maybe I'll just do some kind of test examples for you, okay, to see if you're following along. So first we can ask, what's the open interval AA equal to? And what is the closed interval AA equal to? Okay, so I'll pause here for a second. Okay, so the open interval is the empty set, okay? And this is because, well, there's no, in particular, well, I'll just write it like this. By trichotomy, you can't have a being greater than x and a being less than x, because that would imply that x minus a is both positive and negative. On the other hand, you can have this is just the element a, because a is less than or equal to a, so this is satisfied. Okay? So I think it's actually a pretty natural place to stop here, but maybe I'll just define or give you an idea of what we're going to do with these. It's similar kind of philosophically to what we've been doing with the Archimedean property, right? The whole game that we've been kind of playing in this lecture is if I say I want to get 0, then I can find a sequence of natural numbers which are getting closer and closer. So I'm kind of zooming in to this element 0, and I could have chosen another real number, that would have been fine. I could have but you're zooming in using numbers that you kind of understand. Okay? In the same way, we can zoom in on a real number by taking a sequence of nested intervals. Okay, so in particular, I'm going to look at an interval I1, which contains I2, contains I3, and so on. And so what this looks like is we start with one interval, then we take another interval, then a third one inside, and then we just let this process continue. Okay? So, for example, what we did before is very similar to looking at the interval 1 over n. Right? So I could look at interval from 0 to a half, from 0 to a third, and so on. Okay? So this way of choosing numbers getting closer and closer to 0 is similar to choosing intervals that are getting shorter and shorter. Okay? So that's what we kind of want to think of this. So we think of these intervals as zooming into 0. And in particular, it's true that if I look at the intersection of all these closed intervals, n equals 1 to infinity, I get precisely 0. Okay? So we're going to see that this is kind of going to be another useful way to think of the real numbers or approximate real numbers is by thinking of them as intersections of nested intervals. Okay? So that's coming up next week. So, thanks.